So hello everyone, my name is Nick Zogbi. I'm a first year PhD student in Professor Incorvia's group, and I'll be talking today over voltage controlled magnetic tunnel junctions, also known as VCMTJs. So the main component of how you can actually control MTJ's magnetation and state is by using VCMA, also known as voltage controlled magnetic anisotropy, in which what this does is it actually changes the interfacial magnetic anisotropy due to an applied electric field. So you can actually see that in the figure on the right, in which as it's closer to the Fe oxide interface, the magnetocrystalline anisotropy energy is actually a little bit lowered for the blue line, which is when there's an applied electric field compared to the red line. Then as it goes farther and farther away, the anisotropy starts to even out. So this effect mainly originates due to the hybridization of the 3D orbitals of the transition metal and the 2D orbitals of the oxide. So because of this, these will change the density of states of the iron atom, which also will change the Fermi level of this atom, which causes a change in the number of Bohr magnetons, which is why there is an effect of change in anisotropy energy. So because of this, and because it's an interfacial effect, VCMA devices actually have to have thin ferromagnetic layers. And that's mainly because we want the electric field to penetrate it all and actually cause the whole anisotropy to change. And if it was a thicker material, it wouldn't cause any change. So we actually wouldn't be able to use the effect. So VCMA is actually modeled into an equation, which is shown here, where basically the anisotropy at an applied electric field is equal to the anisotropy with no electric field minus the VCMA coefficient times the electric field all over the thickness of the ferromagnetic. So the coefficient is the main term in VCMA that has the primary amount of focus, in which this is because it determines how susceptible the magnetic anisotropy is due to an applied electric field. And that's basically shown on the top right figure, in which basically how you find that is you can plot the anisotropy due to the electric field, and then you'll be able to find the slope, and that would be the VCMA coefficient. So this plot does not show, but there are actually nonlinear characteristics to VCMA, in which basically what that's saying is the anisotropy will not be going to zero. It does start to bottom out, in which that normally happens when it goes plus or minus greater than plus or minus 1 in the graph too. So there have been a couple of methods that have actually been conducted that will be able to enhance the VCMA coefficient, in which a couple are listed here, in which some of them include modulating the free layer thickness, in which normally if you have a smaller free layer, it will increase the coefficient. You can also increase or decrease the MgO thickness, but that is a little bit of an iffy thing to do because that also will change the amount of TMR for the device. You can also add Mg transition layers between the free layer and the MgO, and that will just make it so that a higher coefficient and there will be less dead layers in the ferromagnetic material. And also you can do annealing temperatures based off of when you're actually creating the MTJ device. So one of the last things is actually using ionic materials in between the MgO and the free layer. However, this as you can see, it has a high coefficient, but it's not as desirable as all the others because ionic materials are charge trapping. So if we were to actually implement this into devices, instead of it being almost instantaneous like they are for normal devices without ionic materials, this will instead cause the change in magnetic anisotropy in the milliseconds. So how this can actually be implemented into MTJs is by using VCMA to the magnetic anisotropy, which will in turn reduce the energy barrier for switching. So two devices can actually be realized through this, one of which is STT-associated VCMTJs, and the other one is precessional VCMTJs. So to actually have the switching due to anisotropy, an external magnetic field is required just so that precessional movement of the magnetic moment is actually achieved, such that it will be starting to spin around due to spin orbit coupling and be able to switch due to momentum. So due to this, and using voltage instead, we're able to modify and improve some of the parameters to MTJs, which those include the write energy, the writing speed, and the endurance. And one of the main key things is endurance, is because we actually aren't passing, we're barely passing any current through, and the only time is actually when it's STT is switched. So the last equation is actually is the critical voltage that will require switching, in which basically what this is saying is if you have a voltage higher than this, it will cause precessional switching. However, if you have a lower voltage, the energy barrier is lowered, but there is still a gap between the two states of the MTJ. So the first scheme is SCT assisted VCMA, or VCMTJs. And that's basically what you do is you will be able to reduce the energy barrier in the MTJ for switching, then pulse a small amount of SCT current into the MTJ so that it will have a lot more reduced amount of energy compared to that of just SCT MTJs. So this scheme is actually deterministic switching, but it has a little bit of a complex timing scheme because you'll have to do a VCMA pulse, and then immediately after you'll have to do an STT pulse, in which the total time of this is around 2 nanoseconds. So it's about normal to STT switching, but the main component is that you do have less energy to it. So one downside of this though, is if you were to increase the amplitude of the voltage applied, it does increase the probability, but there's a lot more precision to the pulse times, and that's basically because the energy barrier is lowered a lot. So if you have a lower energy barrier, it'll cause a little bit more issues to STT switching. So the other form of VCMTJs are precessional, in which that basically is meaning that the magnetic moment will switch thermally, in which that actually has 100 degrees magnetization switch, no matter what type of bit is stored inside the MTJ. So because of that, you're able to achieve a sub-nanosecond timing scheme in the writing. But because of that, you also have to have a complex write operation in which you have to read before you do a write. That's basically because whenever you apply a voltage, it will switch the device. So if you were to write a 1, but the bit was already stored a 1, you actually have to read it before writing it just to make sure you're actually writing the correct thing. And then with higher VCMA coefficients, the pulse timing is a lot more constrained. And that's mainly because if you have a higher VCMA coefficient, that means it's more susceptible to the anisotropy, which means the moment will change quicker. And because of that, you will have to have less pulse time or less of a pulse width such that it can actually switch and not come back to the original state. So in conclusion, the primary focus of VCMA is on enhancing the VCMA coefficient, in which this can be used for VCMTJs because it will be able to reduce the writing energy for it. But for VCMTJs, with the increase in the VCMA coefficient, it will have a lot of precision in the precise pulse times, and also it requires complex switching schemes, which is one of the key downsides to it, and that's actually why it's not really implemented in most MRAM. So just as a little fun example, VCMA is not completely useless because it can actually be used, which is shown here, as a way to propagate domainals just based off of how you have your electrode set up. And also it can be shown to do logic, but also trap the domainals due to a minimum anisotropy. So that could still be used for memory applications in which you could have racetrack memory and actually be able to store your bits with domainals instead of having to do it within an MTJ itself, so that we can, instead of having to do it with precessional or SCT associated, it can be done by domainal movement.